Chapter 11, An Introduction to Calculus with a specific focus on limits. Now the first thing we need to address is what is calculus. My original intent was to take some time right here and explain what calculus is, where it comes from, what we're going to use it for, but instead of reinventing the wheel, I figured I've got the whole internet available to me. What I want you to do right now is pause this video and watch this one right here. What is calculus? I stumbled upon it recently and I thought they did a really good job of explaining what calculus is in a short 3-minute video. They also have a whole bunch of other resources available to you after watching that video. I highly recommend bookmarking it, subscribing, saving that particular channel to come back and look at later. And then once you've watched that video, come back to this video and we will proceed. So did you watch it? Seriously, pause the video right now and watch what is calculus. Alright, so at this point I assume you've watched the video what is calculus. If you're interested and have some spare time and want to know more about the Leibniz-Newton debate, feel free to watch the calculus controversy, another quick little video that explains all about who invented calculus or who really invented calculus. Just some interesting background knowledge. Other than that, let's go ahead and proceed on to what is a limit. Now, a limit is kind of like the bridge concept between pre-calculus and calculus. It's the last concept that can really be considered pre-calculus, but it's also the first concept that is really considered calculus. It is the concept that bridges the gap between the algebra trigonometry-based world and the calculus-based world. Now, to explain what a limit is, I go back to Archimedes and his attempt to estimate the value of pi. Now, what Archimedes did was he recognized that pi is simply the ratio of the circumference of a circle divided by its diameter. In other words, if I take the distance all the way around a circle and then divide by the distance across the circle, no matter how big or how small the circle is, that gives me the exact value of pi. The difficulty is actually measuring those distances. Measuring the length of the diameter, a straight line, not so hard. Pull out a ruler, you can do it. But measuring a curved distance, such as the distance around a circle, is a little bit more challenging. So what Archimedes did is he came up with a simple method. Start by making the diameter equal to 1. By making the diameter equal to 1, calculating pi becomes so much easier because it's now basically just whatever the circumference of the circle is. Now this doesn't do away with the difficulty of measuring the curved length of the circle, but to get around that problem, we simply inscribe a polygon. Inscribe a polygon inside the circle, and then the perimeter of that polygon is roughly equivalent to the circumference of the circle. Therefore, the perimeter is an approximate value for pi. Now, of course, it's not the exact value of pi. The polygon is a little bit too small to represent the actual circumference of the circle. But what we can then say is the perimeter is not the exact value of pi, but the perimeter can be described as a lower bound of what pi actually is. To get the upper bound, draw a polygon on the outside. If we have a polygon on the inside representing an answer that's too small, and a polygon on the outside of the circle representing an answer that's too big, then we can say that pi is between the perimeter of the inside polygon and the outside polygon. In other words, inscribed versus circumscribed polygons. So Archimedes was able to estimate the value of pi using this method, but he didn't stop here. Notice my polygon has 1, 2, 3, 4, 8 sides. Well, if I increase the number of sides, then that distance around the polygon, the perimeter, is going to get closer and closer to the distance around the circle, the circumference. See what I mean here? Here's a 6-sided polygon, diameter 1. The inscribed perimeter is 3.0. The circumscribed perimeter is 3.4641. As I increase the number of sides of the polygon, here I've increased to 12 sides, notice the gap between the polygon and the circle gets smaller and smaller. So here the inscribed perimeter is 3.0. 12 sides, the inside perimeter increases to 3.1. The circumscribed perimeter decreases from 3.4 to 3.2. As I increase the number of sides, notice 24-sided polygon now is 3.1326 to 3.1597. Increase it to 48. Increase it to 96. As I increase more and more sides to the polygon, the distance between the inscribed perimeter and the circumscribed perimeter gets smaller and smaller and smaller. And notice we start to approach an agreed upon value of 3.14. Now 96 sides, this is where Archimedes stopped, but I could keep going. I could keep going further and further and further. Archimedes stopped here because he was limited by the tools that were available to him 2,000 years ago, but he failed to make that last little leap, that last little jump, that last step to the idea that if I increase the number of sides infinitely, not only would that give me a close value for pi, that would give me the exact value of pi, because if I have a polygon with an infinite number of sides, that polygon is no longer a polygon, it's a circle. A circle is simply a polygon with an infinite number of sides. Archimedes lacked that understanding of infinity. The idea in the modern world that we now have is that as I increase the number of sides to infinity, which I can never actually reach, I get the exact value of pi. That concept of approaching a number that I can never actually reach, that is what the concept of a limit is. So the big idea here is that the perimeter of the polygon can be used as an approximate value of pi. As the number of sides approaches infinity, the perimeter of the polygon approaches the circumference of the circle. A polygon with an infinite number of sides would give an exact value of pi. The limit of the perimeter as the number of sides approaches infinity is pi. In other words, when I started with 6 sides, the inscribed perimeter was 3. Then it goes to 3.1, then it goes to 3.13, then it goes to 3.1394, then it goes to 3.14. As I increase the number of sides, I know from my understanding that pi is 3.14159, I know that this number right here is just going to get closer and closer and closer to the exact value. It's never going to pass the exact value. It's just going to be limited by the exact value of pi, 3.14, whether I approach from the inscribed perimeter or from the circumscribed perimeter. The limit of the perimeter is as the number of sides approaches infinity is exactly pi. A limit is a value that we are approaching as the number of sides approaches infinity. Now this chapter on limits we're going to break into 5 parts. We're going to start with evaluating limits. Then we're going to look at one-sided limits. Then we're going to look at limits involving infinity. We're going to continue on to a discussion about continuity. And then finally an introduction to the derivative, which is the likely point where your calculus class will pick up. So let's jump into it with Chapter 11, Part 1, Evaluating Limits. So another informal way of describing what a limit is the intended height of a function. Not the actual height, but the intended height. Now anytime I refer to height, I'm referring to the y value of the function. Height would be how high or how low below the x-axis the graph is, which is represented by the y value. So consider this function right here. Now notice this function is a nice smooth continuous curve, probably the graph of a polynomial function. Sometimes I'm going to refer to this as a well-behaved function, because everywhere along the curve it's behaving in a reasonable manner. It's not jumping out up or down, going in a drastically different direction. It's just going in this nice smooth flowing curve forever and always. So if I ask you what is f of 1, keep in mind what I'm asking is what is the y value when x is 1. I simply look at the graph. Here's x equals 1. Here's a vertical line representing x equals 1. And the curve passes through that vertical line at a height of -1. So I would say f of 1 is -1. In other words, the exact value of f of 1 is -1. I could do the same thing at f of 3. So at x equals 3, I look at the graph. I see that the graph reaches a height of 2. So I say the exact value of f of 3 is 2. But what about when it's not so well behaved? Look at this function right here. Notice we have almost exactly the same curve, except at x equals 3, there's a hole in the graph. So basically the graph is going along its merry way, and all of a sudden when it gets to x equals 3, it pops out of existence. And then as it passes through x equals 3, it reappears back in existence and goes along its merry way as if nothing ever happened. So in this case, when I ask what's the height at x equals 3, because there's a hole in the graph, I would be forced to say undefined. There is no height at x equals 3 because there's a hole in the graph at x equals 3. On the other hand, if I do something like this, there's still a hole at x equals 3, but there's also a closed point slightly below that hole. So in this case, when I ask what's the height at x equals 3, I would say that the height is 1, because the coordinate along that vertical line at x equals 3 has a height of 1, not a height of 2. So then I ask my new question. involving a limit representing the intended height. And I read this, the limit as x approaches 3 of f of x. So what is the intended height as the graph gets arbitrarily close to 3 for the given function? And when you're evaluating a limit, think about covering up the entire vertical line at x equals 3. You don't see this dot, you don't see this hole. If I look at everything around x equals 3, it looks like a nice smooth continuous curve, but then when I look at x equals 3, I've got this craziness going on. A limit or intended height is like asking your friend what his favorite restaurant is, but without actually asking what his favorite restaurant is. Instead of asking what's your favorite restaurant, look at his credit card receipts. If he's always going to the same restaurant, then that implies that that's his favorite restaurant. But of course, maybe it's not his favorite restaurant. Maybe he likes going somewhere else. He just likes paying at this one location because he's crazy. The point is, what the actual restaurant is, what the actual height is not relevant. What's relevant is what are the clues dictating the actual height would be. And in this case, the curve is approaching a height of 2 from both directions. So I would say that the limit or the intended height as x approaches 3 is 2. Even though the actual height is 1, the intended height is 2. So for well-behaved functions or continuous functions, we can expect that the actual height and the intended height are going to be the same. So we say that the limit as x approaches a of f of x equals f of a would describe well-behaved functions. So what that means is, if you're trying to figure out the intended height of a function, and you know that function is a well-behaved or continuous function, you can simply evaluate the actual height, f of a, and have it represent the same answer. So let's look at what I mean by that. Notice what we have here. We have a polynomial, we have a radical function, a rational function. All of these are considered continuous functions over their domain. Polynomials are smooth and continuous, radicals are smooth and continuous, rational functions are smooth and continuous, as long as you were within their domain. For example, this rational function at x equals 3, we'd have something crazy going on. But for any other number other than x equals 3, it's smooth and continuous. So we can evaluate these simply by doing what I call direct substitution. Simply take the x value, plug it in, get your answer. In this case, the limit as x approaches 2 is just as easy as evaluating what is f of 2, and in this case, f of 2 would be 10. So not only is the actual height 10, the intended height was 10. So why don't you give these a try, pause here, play when you're ready. Hopefully you figured out these without a problem. Plug in 0, I get 3. Plug in -1, I also get -1 as my answer. But then this last one, maybe you had a little bit of trouble. Plug in 4, I get -6. The square root of -6 is, of course, imaginary. So then how do I answer the question? Do I answer the question with the imaginary number, or do I answer in some other way? And when it comes to limits, I'm going to answer it in a different way. A limit is an intended height. A height exists on an xy coordinate plane. Imaginary numbers do not exist on a xy coordinate plane. Therefore, we're going to say the answer is D and E. Does not exist. Anytime we evaluate a limit and we get an answer that is either undefined or imaginary, we simply say that the answer does not exist. I would have done the same thing up here if I had asked what's the limit as x approaches 3. 4 divided by 0 is undefined, so I would have said does not exist. So these are what I would collectively call pretty straightforward limits. We evaluate these limits by direct substitution. We plug in the number, we get the answer, we move along on our merry way. Now keep in mind, as we did with the original example of the graph, we don't actually need to know what the algebraic function is. As long as we know that f and g in this case are smooth and continuous, and I know that the limit for f as x approaches 7 is 6, and the limit for g as x approaches 7 is -6, I can add, subtract, multiply, and divide these limits together without hesitation. Again, as long as they are well-behaved functions, that's perfectly fine. Now when we get into situations where they're not so well-behaved, all bets are off. But for these, since they're well-behaved, if I want to evaluate the limit as x approaches 7 of f times g, just multiply your answer for f and your answer for g, and you get -36. Now that we know that we can do this, go ahead and pause here, play when you're ready for the last two. So on the next one, we're going to multiply g times 4 and then add f and g together. So we get -18. And the last one, we're going to subtract and divide, so we'll end up with 1/2. So for all of these smooth and continuous or well-behaved functions, they're pretty straightforward. Direct substitution gets the job done. But not everything is smooth and continuous. Not everything is well-behaved, so occasionally we're going to need some more advanced techniques. So consider the function y equals x squared minus 4 over x plus 2. Once again, we have a rational function. We looked at a rational function a couple of examples ago, and we determined that as long as we stay within the domain, we have a well-behaved function, and thus we can evaluate limits just by direct substitution. For example, the limit as x approaches 1. If I plug in 1, I get -1 as my answer. 1 squared minus 4 on the top would be -3. 1 plus 2 would be 3. -1, final answer. The exact height of the function is -1. The intended height is -1. If I evaluate at 2, limit as x approaches 2. 2 squared minus 4 is 0. Over 2 plus 2 is 4. 0 divided by 4, that's a height of 0. So in this case, the limit as x approaches 2 equals our exact height, which also happens to be an x-intercept of the graph. But when I look at -2, not only do I get 0 on the top, but I also get 0 on the bottom. And here we have a problem. 0 divided by 0. What is going on here? We have a situation where we have two separate rules, two perfectly valid and useful rules that are actually in conflict. I know that anything divided by itself is 1. So is 0 divided by 0 equal to 1? I also know that anything divided by 0 is undefined. You're not allowed to have 0 on the bottom. You can have 0 on the top like we did for this limit, but this time we have 0 on the bottom, which means undefined. And undefined implies that the answer should be D and E. So which rule do I use? Do I use the rule that leads me to an answer of 1? Or do I use the rule that leads me to an answer of D and E? And the correct answer is neither. 0 over 0 is what's known as indeterminate form. Indeterminate in that the answer is not yet determinable. When I see 0 over 0, do not stop. We need to investigate further using more advanced techniques. 0 over 0, indeterminate form, simply means direct substitution was insufficient to answer this question. Let's try something else. Now, something else we can try is the graphical approach. I started my explanation of what a limit was with a graph, and of course we can simply look at the graph, see what the intended height of the graph looks like, and say that the answer to the limit is that intended height. So let's do that. Now at this point, if you haven't done so already, go ahead and grab your graphing calculator, because I want you to go ahead and graph this function on your own first. So I'm going to be using a TI-8384 series graphing calculator, but this will work with any calculator. So take a moment, graph it in your calculator, play when you're ready. So when you graphed it in your calculator, hopefully you got something that looks sort of like this. If you didn't get exactly what I got, maybe you need to, if you're in the, again, TI-8384 series, you'd hit Zoom 6 to go to your standard viewing window, and you'll get something that's probably a little bit bigger than mine. Or you can just, count up the tick marks and see what my actual window is and adjust your window manually. The point is, you should see something that looks like a line. Because it is a line. X squared minus 4 over x plus 2 may not be what you're accustomed to the equation of a line looking like, but look at the graph, it's a line. Now if I try direct substitution using my calculator, that's just a matter of tracing -2 on the calculator. So go ahead and give it a try, hit trace -2, enter, and see what happens. When I trace -2, notice it doesn't give me a y value because, again, there is no y value associated with -2. Just like when I did direct substitution by hand, I got indeterminate. The calculator also agrees that it doesn't know what the answer is. At -2, there is no answer. So then the question is, what does the answer look like? As I approach that vertical line representing x equals -2, it looks like the height is -4. And since the graph is approaching that height of -4 from both sides, then I can say that because it looks like the graph is approaching -4, I can say that the limit is -4. So when our direct substitution technique fails, we can look at the graph and evaluate the limit visually. Another option would be numerical. When I say numerical, I'm referring to a table of values. Now, of course, we could do a table of values by hand, picking random x values close to -2, plugging in and evaluating, but we have our calculators. Let's use our calculators. Simply hit second table set. That's going to get us to our table setup menu. Since I'm trying to evaluate the limit close to -2, I'm going to start my table at -2.3, a value very close to -2. When it comes to evaluating limits, the closer you are to the intended value, the more accurate you're going to be. So I'm going to start at -2.3, and I'm going to take a step size of 0.1. That triangle right there is the Greek letter delta. Delta, when we're in math and science, always represents change. So this would be the change in table, aka step size. So then I'll hit second table. And what it'll do is it'll automatically create an XY table for me using the function that hopefully I still have typed into the Y1 screen. So notice as the x values increase from negative 2.3 to negative 2.2 to negative 2.1 to negative 2, the y values are going from negative 4.3, negative 4.2, negative 4.1, and then at negative 2 we get an error. Again, that's the same thing as if I traced negative 2, I got no answer. The calculator has no idea what to do at negative 2. But if I look at the values as they approach negative 2 from both sides, hopefully you would agree that it looks like if that error wasn't there, it would probably have said negative 4.0. So again, it still looks like negative 4 is the intended height. Therefore, the limit is still negative 4. So I've got a graphical argument as to why the limit is negative 4, and I've got a numerical or tabular argument as to why the limit is negative 4. Problem with graphs and tables, though, is that they're not always the most accurate methods. Graphs, very easy to use my human eyes to be off by a little bit. Same thing with tables. Maybe if I went a little bit closer to negative 2, instead of using negative 2.1 or a step size of 0.1, what if I used a step size of 0.01 or 0.001? Maybe something completely crazy is going on between negative 2.1 and negative 1.9 that I'm not seeing because I'm not choosing a small enough step size. If direct substitution doesn't work, graphs and tables are there to help you, but nothing beats the algebraic approach. When direct substitution doesn't work, the algebra approach should be your next step. Before you go to graphs and tables, try the algebra. And what I mean by algebra is let's try simplifying. X squared minus 4. Hopefully you notice x squared minus 4. That's a difference of squares, which means we can factor. X squared minus 4 factors into x plus 2, x minus 2. X plus 2 and x plus 2 cancel out, leaving behind x minus 2. Now notice the graph of this function was a line because the simplified form of this function is a line, x minus 2. This time, though, when I plug in negative 2, there's no x plus 2 in a denominator to cause problems. So when I plug in negative 2, I get an exact answer of negative 4, which means that the limit is indeed negative 4. Not based on my best guesses looking at a graph or a table, but indisputably based on the algebra. So a quick summary of evaluating limits: always start with direct substitution. If it's a well-behaved function, you'll be able to plug and chug, get an answer directly, and you're done. But if you plug and chug and you get indeterminate, either 0 over 0 or a form we're going to see later on, infinity over infinity, that simply means that you need to investigate further. First suggestion is always the algebraic approach, but if the algebraic approach is either not possible or inconclusive, then try either a graph or a table. So now that we know all that, why don't we give these a try? Go ahead and take a look at each one of these in turn. Pause here, play when you're ready. All right, looking at the first one, limit as x approaches 0 of x squared plus 2x over x. Now again, I said first step should always be direct substitution. Hopefully you tried direct substitution first. Now when I try direct substitution, plug in 0 to the top, plug in 0 to the bottom, I get 0 over 0, our indeterminate form. Now, of course, if you skip that direct substitution and just went straight to factoring, you're going to get the right answer anyway, but please always start by direct substitution. You cannot start with the assumption that you're going to have to factor. If I had asked limit as x approaches 1 on this problem, and you started with factoring, you're still going to get the right answer. But boy, are you wasting time, because if I just plug in 1, I've got my answer right there. If I factor it, simplify it, and then plug in 1, I'm going to get the same answer as if I had just tried direct substitution. Always start by direct substitution to confirm that you don't have to waste time and that you don't have to just plug in the number, get the answer, and move on. Direct substitution first, I get indeterminate. Indeterminate means keep going. Let's try algebraic analysis. I notice that the top is easily factorable by pulling out an x. So that's what I do. I pull out the x cancels with the x on the bottom, leaving behind x plus 2. I'm now finished simplifying. Let's reapply the limit, plug in 0, and I get 2. So the limit of this function is 2. Let's do it again. This time the limit as x approaches negative 2 of x squared minus x minus 6 all over x plus 2. If you haven't done this one already, hit pause and then play when you're ready. So again, we start by plugging in negative 2. If I plug it into the top or the bottom, I'm going to get 0 over 0, indeterminate form. So let's factor it out. If I look at the top is going to factor into x minus 3, x plus 2. The bottom is going to factor into x plus 2. X plus 2's cancel out, leaving behind x minus 3. Final answer, negative 5. The limit as x approaches negative 2 of the given function is negative 5. Let's keep going. Try it again. Limit as x approaches 3 of x squared minus 9 over 2x squared minus 5x minus 3. Pause here if you need, play when you're ready. Hopefully you're starting to get the hang of this. If I plug in 3, I get 0 over 0, which is indeterminate. The top is a difference of squares. Factor it into x plus 3, x minus 3. The bottom factors into 2x plus 1, x minus 3. X minus 3 cancels out. We now have a new rational expression. If I plug in 3, no indeterminates, I get the exact answer of 6/7. Next one on our list, limit as x approaches 1 of x squared plus 1 over x minus 1. Pause here, play when you're ready. As always, I'll start with direct substitution, plug 1 into the top and the bottom. Now on the bottom, 1 minus 1 is going to be 0, but on the top, 1 plus 1 is going to be 2. This time, I don't get 0 over 0, I get 2 over 0. 2 over 0 is not indeterminate. 2 over 0 is undefined. This is not a problem that requires algebraic analysis. This one, we are done. The answer is D and E. When I get 0 over 0, that means there's a hole. A hole means there's an answer. I need to figure out what the answer is. 2 over 0 is not a hole. A number over 0 is an asymptote. An asymptote has no limit. This is undefined, thus the answer is does not exist. This is again my point as to why you should always start by direct substitution, because maybe the answer is already staring you in the face. Don't do all the work of trying to factor when you don't need to, especially on this one, because this one was not factorable at all. X squared plus 1 is not a difference of squares, it's a sum of squares. X squared plus 1 is not factorable. If you factored that into x plus 1, x minus 1, and then canceled out the x minus 1s, you did it wrong. You got the wrong answer because you factored incorrectly. Direct substitution first. If you have an answer, you're done. How about this one? Here's one that's a little bit different and a little bit more challenging since we are now calculus level students. Limit as x approaches 4 of 1 over x minus 1 over 4 all over x minus 4. If you want to try this one on your own, go ahead and hit pause here, give it a try, and then play when you're ready. As always, I'm going to start with direct substitution, plug in 4. So if I plug in 4 right here, 1 over 4 minus 1 over 4 is 0 on the top, 4 minus 4, 0 on the bottom, indeterminate. Indeterminate means let's try an algebraic simplification. Now, in this case, factoring is not going to be my goal. There's nothing to factor here, but I still need to simplify. I have a fraction inside a fraction. We've seen this type of problem enough times throughout our algebraic career. When I have a fraction inside of a fraction, my best suggestion is to get rid of the inner fraction. Get rid of the fraction on the top by multiplying through by the denominator, by the extra denominator. So if I multiply top and bottom by x, that would get rid of this fraction. If I multiply top and bottom by 4, that would get rid of this fraction. So in other words, let's just multiply top and bottom by 4x. So essentially what I'm doing is multiplying top and bottom by the common denominator of the fractions on the top. So if I multiply by 4x onto this guy, I'm just going to be left with 4. If I multiply by 4x onto this guy, I'm just going to be left with x. So that would give me 4 minus x on the top. And notice on the bottom, I did nothing. I'm not going to multiply through on the bottom. Of course, it's perfectly legal to multiply through on the bottom, but then it's going to lead us to what we did earlier. We're going to need to factor everything out, so just leave it in its factored form. No need to multiply through on the bottom, because the bottom wasn't my issue, it was the top. Now, usually what I have here is a common factor between the top and the bottom that I can just cancel out. But here it's not quite common. It's 4 minus x on the top, x minus 4 on the bottom. Well, the good news is we've got an easy fix for that. If I have almost common factors except they're backwards from each other, just simply factor out the negative on one of them. I'm going to go ahead and factor out the negative on the top. If I factor out a negative off of a positive 4, that's just going to leave me a negative 4. If I factor out the negative here, that's going to leave me with a positive x. So in other words, positive x, negative 4, now I have the same thing top and bottom. I can be sure that I'm right by redistributing the negative. Negative x, positive 4, which is exactly what I have here. So if you need to reverse the order of a subtraction problem, just factor out a negative, which allows us to cancel, leaving a negative 1 on the top, 4x on the bottom. Apply your limit, negative 1 over 16, final answer. Now, keeping that method that we just used in mind, give this one a try. Pause here, play when you're ready. So once again, I have extra fractions on the top, so fractions within a bigger fraction. Always going to start by direct substitution to justify that it's indeterminate, and thus I need to use fancy techniques. So the fancy technique that I used on the last one, which I'm going to try again on this one, is I'm going to multiply top bottom by the common denominator of the top. So I'm going to multiply by x plus 6 and by 6. So multiply by 6 and x plus 6. Distributing on the top leaves me with 6 for this fraction and x plus 6 for this fraction. Now notice when I wrote that x plus 6, I put it in parentheses. That is incredibly crucial that I put that in parentheses, because remember, we are subtracting. I'm not just subtracting one term, I'm subtracting the entire quantity. I'm not just subtracting the x, I'm subtracting the quantity x plus 6. If I don't put those parentheses, then this plus 6 is going to remain a plus 6, and the problem's not going to be able to move forward. But by keeping those parentheses in and then distributing the negative, look what happens to the 6's. They cancel out. If I don't put those parentheses, basically I have to stop here and give up. So by canceling the 6's on the top, that now allows me to cancel the x top and bottom, leaving behind a negative 1 on the top and then a 6, x plus 6 on the bottom, plug in 0, negative 1 over 36, final answer. So we've looked at some indeterminate limits involving factoring. We've looked at some indeterminate limits involving fractions. Let's look at some indeterminate limits involving radicals. Now, if you want to try this one on your own, feel free. I'd be very surprised if you figure out the correct technique on one of these guys, but you are more than welcome to give it a try. Pause here, play when you're ready. Otherwise, let's go ahead and jump into it. As always, direct substitution is our first step. Plug in 0, I get 0 over 0, indeterminate. No big surprise here. But the key to dealing with limits involving radicals is remembering a basic property of radicals, and it's not the fact that squaring a radical gets rid of the radical. All right? I know that if I take the square root of a and square it, then the radical goes away and I get a as my answer. But here we don't just have a radical, we have a radical minus a number. In other words, we have a binomial. So we have something that looks more like this, square root of a minus b. And if I make the mistake of just squaring this, what I'm really doing is multiplying it by itself. And if I were to multiply that through, I get an answer that looks like this. So in other words, I get an answer that's way uglier than what I started with. Keep in mind, in this case, it would be x plus 1. So this would be x plus 1 minus 2 times the b value, which is 1, over the square root of x plus 1 plus 1 squared. I would have rather just figured out the limit on what I started with. The key to getting rid of a radical that's part of a binomial is not squaring the whole thing, but multiplying by its conjugate. Square root of a minus b times the square root of a plus b produces a difference of squares. Square root of a squared would be a, and then the the b value squared would just be b squared. In other words, I've got a difference of squares which factors into square root of a minus b, square root of a plus b. Therefore, the multiplication of square root of a minus b, square root of a plus b foils out to a minus b squared. Multiplying by a conjugate gets rid of the radical, which leads us to our approach on this one. I start with recognition that I have a radical involved in a binomial. The easy way to get rid of that radical is to multiply by the conjugate. The conjugate of the square root of x plus 1 minus 1 would be the square root of x plus 1 plus 1, and whatever I do to the bottom, I have to do to the top. So on the top, I'm just going to leave it in its factored form, x times that entire quantity, but on the bottom, I'm going to multiply through, recognizing that all I really have to do is take the square root of x plus 1 multiplied by the square root of x plus 1, which is the quantity x plus 1, minus the b value squared, 1 times 1, which is 1. So I ended up with this. X plus 1 technically should be in parentheses, but because it's there's nothing to distribute across that parentheses, I went ahead and dropped them, minus 1. So the 1 minus 1 cancels out on the bottom, which allows us to cancel out the x's, which leaves us with something much easier to approach. Plug in 0, and I get 2. Final answer, 2. When I have a limit that's indeterminate involving a binomial of a radical and a radical, or a radical and a non-radical, multiply by the conjugate to get rid of the radical. Using that approach, try it again. Pause here, play when you're ready. All right, once again, we plug in the limit. We get 0 over 0, indeterminate. The approach that we tried on the last one should work on this one as well. Let's multiply by the conjugate of the top. Instead of 2 minus radical x plus 3, how about 2 plus radical x plus 3? Multiplying through on the top is going to give me the difference of squares, 2 squared minus the square root of x plus 3 squared, or just x plus 3. Notice this time I made sure to put that x plus 3 in parentheses because it immediately follows a subtraction symbol. Also notice on the bottom, I did nothing. I didn't multiply through, I left it in its factored form. Simplifying the top a little further is going to give me minus x minus 3, so 4 minus 3 gives me 1. I now have 1 minus x on the top, x minus 1 on the bottom. Remember from a few problems ago, we can fix this problem by simply factoring out a negative out of the top, or just cancel it out, leaving behind a negative 1. We now have negative 1 over 2 plus square root of x plus 3. Plug in 1, we get our final answer of negative 1/4. Now for something completely different. Limit as x approaches 0 of sine of x over x. Here we have a limit involving a trig function. If I start with my normal approach, plug in 0, I get 0 over 0. I see I have my indeterminate form, so then let's try my algebraic approach. But then I get stuck. How do I approach a trig function algebraically? And I'll tell you, your guess is as good as mine on this one. How I do this algebraically, I have no idea. But good news, algebra wasn't our only option. Maybe let's try a graphical approach. If I pull out my calculator and I graph sine of x over x, I'm going to get a graph that looks something like this. As x approaches 0, it looks like we have a height of 1. Now, of course, if I trace 0, I get undefined, or I get an indeterminate number. I get no answer. But I can still look at the graph and it looks like 1. So I'm going to say that the limit is 1 because it looks like the graph is approaching 1 from either side. The intended height looks like 1. All right, but again, graphical approach is not my only option. I could try a numerical approach. Remember, I could use the second table set feature. I would probably suggest starting at a negative 0.3 since my intended value is at x equals 0 with a step size of 0.1, and then hit second table to see my table of values. So I see 0.985, 993, 0.998. From both sides, it looks like it's approaching 0.999999 or 1. So my numerical approach, my table of values, confirms that my answer looks like it's 1. Now at this point, I've kind of run out of methods. My algebraic approach was, I have no idea. My graphical and numerical approach seem to confirm that the answer is 1, but there's another approach that we have yet to talk about, and that's the geometric approach. And putting all cards on the table, I'm not actually going to require that you know this approach, the geometric approach to a limit. I'm simply trying to confirm that the sine of x over x, the limit as x approaches 0, the sine of x over x is 1. Because this particular limit is going to come up a lot, and I don't want to build on top of this limit using a shaky foundation that I'm pretty sure the answer is 1, but I never actually confirm that the answer is 1. I'm going to go through the geometric approach simply as a means to an end. You're not going to be required to memorize this approach. You're not going to be required to use this approach in the future. This is simply an opportunity for you to kind of sit back and relax and follow my method, and we're going to confirm that the sine of x over x is in fact 1. So I'm going to start by imagining a circle. Now I'm just going to focus on the first quadrant of that circle, and there's a point P on that circle within the first quadrant. Now I hope you all agree that it's perfectly possible to draw a triangle within the first quadrant of that circle which intersects the circle at that point P. We now have an angle x in standard position, and I'm going to go ahead and define the radius of this circle to be 1 for convenience. Radius could be any number it wants to be. Everything's going to reduce out anyway. I'm just going to make it 1 to make things simple. Now the first thing I'm going to want to determine is what the height of point P is, in other words, the opposite side of the triangle. Now to do this, I'm just going to set up a simple trig ratio. I know that the hypotenuse of the triangle is 1. I'm looking for the opposite side of the given angle, so I can simply define that the sine of x is the opposite over the hypotenuse. The opposite is what I'm looking for, but I know that the hypotenuse is 1. Therefore, the sine of x is the opposite side. So I'm going to go ahead and redefine the opposite side simply to be the sine of x. So for this triangle, the angle is x, the hypotenuse is 1, and the opposite side is the sine of x. Next, I'm going to draw a larger triangle. Now this larger triangle is still going to go through point P, but it's actually going to go entirely outside the circle and then connect down here. I'm going to try to figure out the same information I did before, the opposite side of x, but this time it's not going to be the sine of x because the hypotenuse of that triangle is no longer 1. I actually have no idea the length of the hypotenuse of this triangle, but I know that it's definitely bigger than 1. But what I do know is that if this length is 1, then this length right here is also 1, which is going to be the adjacent side. So if I'm looking for the opposite and I know the adjacent side, then I'm going to use a tangent ratio. Opposite side is unknown, but now the adjacent side is 1. Therefore, the opposite side for the bigger triangle is going to be the tangent ratio. Now, given this information, I'm going to do one more thing. I'm going to connect a segment from point P down to this point down here for no obvious reason, but all will soon become clear. And one last thing, let's go ahead and label our corners point A, point B, point C for convenience. Now, what we've established here are 3 distinct regions. The first one is the small triangle APC. And what I'm going to do is I'm going to establish that the area of that triangle APC is less than the area of the sector APC, which is still smaller than the area of the larger triangle ABC. Hopefully that's pretty obvious that the small triangle has a slightly less area than the full sector, which has a smaller area than the big triangle. So I'm simply establishing a fact that we all know to be true. Now, to find the area of triangle APC, area of a triangle is 1/2 the base times the height. I know the base of the triangle is 1, and I know the height of the triangle is the sine of x. So then the area of triangle APC can be said to be 1/2 times 1 times sine of x. In other words, sine of x over 2. The area of the sector, I'm sure you don't remember the area formula for a sector, so I'll remind you up here. Area of a sector is 1/2 the angle times the radius squared. In this case, the angle is x, and the radius is 1. So it would be 1/2 times x times 1 squared, or x over 2. And then the area of the larger triangle, just like the area of the smaller triangle, 1/2 base times height, 1/2 times 1 times tangent of x, since the height of the larger triangle is tangent, not sine. So what we have here is a statement that sine of x is less than tangent. Of course, that comes from simplifying the multiplication and canceling out the 2's on all 3 area formulas. So I've now established, based on the given information, that the sine of x is going to be less than tangent of x. Again, it still may not be obvious what I'm doing here, but bear with me. Now, for simplification purposes, I'm going to go ahead and convert tangent to sine over cosine because I don't like having 2 completely different trig functions. I want to get them as close as possible to just one trig function throughout. So converting tangent to sine over cosine gets me the same trig function here and here, but then I still have cosine. I'm then going to go ahead and divide out the sine on all 3 pieces. As long as I do it to all 3, it's perfectly legal. So if I divide everything by sine, sine over sine cancels to 1. I then have x over sine here. And then keep in mind here, sine over cosine divided by sine, it's just the sines are going to cancel out, and we're left with 1 over cosine. Now you may have an idea of why I did that. The original question, if you've forgotten already, was the limit as x approaches 0 of sine of x over x. Now I still don't have a sine of x over x here, but now I have x over sine. If only I could flip this upside down. If I could flip this upside down, instead of it saying x over sine, it would then say sine over x. I could then have a statement that relates back to my original question. Well, good news, I can. I'm just going to reverse. I'm going to take the reciprocal of all 3 sides. Again, as long as I do it to everything, it's perfectly legal. But something I'm going to remind you of that you've probably forgotten is a simple rule that has to do with inequalities. When I take an inequality, such as 1/2 is less than 1, and I take the reciprocal of both sides, 1/2 becomes 2, 1 stays 1. But notice what also happens is that the inequality flips as well. If I flip the fractions, I also have to flip the inequality to remain true. So when I flip 1, it stays 1. When I flip x over sine, it becomes sine over x. When I flip 1 over cosine, it becomes cosine. But the less thans become greater thans. Now that I have sine of x over x, which relates back to my original question, I'm going to go ahead and apply the limit to all 3 pieces. So this centerpiece is my original question. And I'm saying that original question, limit as x approaches 0, sine of x over x, is between the answer to this question and the answer to this question. So the answer to this question, limit as x approaches 0 of 1, limit of a constant, is just that constant. If I plug in 0 to 1, the answer is still going to be 1. If I plug in 0 over here, the answer is also 1 because the cosine of 0 is 1. So what we have here is a statement that says that the limit as x approaches 0 of sine of x over x is between 1 and 1. Think about what I've just said there. The answer is somewhere between 1 and 1. So what's the answer? Obviously, the answer is 1. We call this the squeeze theorem. If we can manipulate a problem, an inequality statement, to be such that my unknown is between two known values, and those two known values are equal, then the unknown value in the middle must be equal to those outer values as well. So by the squeeze theorem, I can say finally and completely and truthfully and irrevocably that the limit as x approaches 0 sine of x over x is and forever will be 1. We justified it graphically, we justified it numerically, we have proven it geometrically. Now this particular limit, I spent so much time on this particular limit because it's going to come up over and over and over again. So what I want you to do right now is memorize it. The limit as x approaches 0 sine of x over x is 1. The limit as x approaches 0 of sine of x over x is 1. Now let's look at a problem. Evaluate the limit as x approaches 0 of sine of 2x over x. Well, here we don't have the exact same format as the original question, so is the answer still 1? Or is the answer something different? If I try my direct substitution method, I get 0 over 0 indeterminate, which means I need more advanced methods. Factoring is not going to work. Other algebraic methods are going to work. That geometric approach would work, but I don't want to have to do it. I want to relate what I have here back to that known value that I just determined. Sine of x over x is 1. So what do I do when I have sine of 2x? Well, let's get fancy. Would you agree that if I multiply top and bottom of the fraction by the same thing, it doesn't change anything? Multiplying top and bottom of a fraction is still perfectly legal. In this case, what I'm going to do is I'm going to multiply top and bottom of that fraction by 2. I chose 2 because that's the number that I have right here. So I'm going to multiply top and bottom by 2. Now keep in mind, I haven't changed anything because 2 over 2 is still 1. But what I can now do is strategically multiply. I'm going to go ahead and take this 2 and move it in to be 2x, but I'm going to take this 2, I'm going to pull it out completely and ignore it. Because a 2 is just a constant, and constants can be pulled in or pulled out and put into problems at will. I'm just going to legally pull that 2 outside the problem and deal with it later. And now what I have is a limit that doesn't exactly match the limit that I learned before, but essentially matches. What's important is not what this says, but that this and this match. It doesn't necessarily have to say sine of x over x. As long as it's the same thing here and here, then I can say that the limit is 1. In other words, the ratio of this guy to this guy has to be 1. So since that's what I have, I can say that, well, this piece right here is 1, but let's not forget about this guy. I still have that 2 up front. Therefore, 2 times 1 is 2. So in this case, the limit is 2. So notice what I'm establishing here is kind of a shortcut. The ratio between the inside of the sine function on top to the denominator is what the answer actually is. Instead of going through all this fanciness or even the geometric approach, just remember this. The limit as x approaches 0 of sine of ax over bx is a over b. So if this is sine of x over x, then a over b is just 1 over 1, so the answer is 1. The ratio between this guy and this guy is the answer. As long as it's this format, we can just jump straight to an answer, a over b. So now that we know that, give this one a try. Take about 3 seconds, answer the question, and then hit play when you're ready. All right, hopefully it's been 3 seconds. You already know the answer. I see that it fits my standard format, sine of something x over something x. Limit is going to 0. If I tried plugging in 0, of course I would get indeterminate, but what a waste of time because the answer is 4/5. As long as it's going to 0, then I can say the answer is just 4 over 5. Now keep in mind, if the answer is not going to 0, or if the x is not going to 0, if x is going to say 1, don't just jump to an answer of 4/5. Direct substitution first. If this were a situation where x was going to 1, then my answer would be sine of 4 over 5. Not 4 over 5, but sine of 4 over 5. If I'm going to 10, it would be sine of 40 over 50. Only when it's going to 0, only when I have the indeterminate form, can I use my shortcut of just whatever this ratio is. So we've got the easy ones. How about the not as easy ones? Go ahead and give these a try. Hit play when you're ready. All right, looking at the first one, limit as x approaches 0 of x plus sine of x over x. If I plug in 0, I get 0 over 0, indeterminate. Now I notice right here, sine of x over x, that's the shortcut right there. That's the limit. It has to equal 1. But I didn't give you a situation where I was adding to the numerator. I only gave you situations where, what if there was a number here? Well, this is easy. I have a monomial denominator. Anytime I have a monomial denominator, break it up. Break it up into 2 fractions. I then have x over x plus sine of x over x. Now, of course, x over x is 1, and sine of x over x is also 1, based on our limit rule. So 1 plus 1 is 2. Final answer, 2. Now here we have, again, the same format, but instead of it being sine, it's now tangent. So does that mean the answer is still 1, or is it something different? The point is, the only thing I know is sine of x over x. I can't just assume that this is the same. I have to relate this back to sine of x over x. Well, good news is I know that tangent is directly related to sine using my quotient ratio, sine over cosine. So I'll go through the needed step of plugging and chugging to start with to prove that it's indeterminate, and then I'll just replace tangent with sine over cosine. In order to make my simplification a little bit more obvious, I'm going to go ahead and rewrite this as 2 separate fractions multiplied together. So instead of the sine over cosine being in the numerator, I'm going to go ahead and pull that numerator off to the side so that it's 1 over x times sine over cosine. I'm going to recognize that this is a multiplication problem, and multiplication can be done in any order. So whether it's x times cosine or cosine times x, it's still the same thing. But now by reordering that multiplication problem, I can clearly see sine of x over x, which is 1. And then plugging in 0 here, cosine of 0 is also 1. So yes, tangent of x over x is also 1. And one more for you to try. Hit play when you're ready. All right, on this one, I wouldn't be surprised if you looked at this initially and thought, oh my gosh, what am I supposed to do? But then, of course, you remembered direct substitution should always come first. When I plug in 0, e to the 0 is 1. Tangent of 0 is 0. Cosine of 0 is 1, so what I have is 1 over 1, which is 1. No fancy techniques needed on this one, just plug and chug, we get our answer.